All right, so here are the solutions for the review or the practice tests for sections 3, 4, and 5. So this is for our test on parabolas coming up. All right, so it asks us to complete the square so that we can put the parabola into vertex form. This is vertex form here. So in completing the square, I need to send my constant term over to the other side. So I'm going to have f of x, and I can change this to y if I want to, but I'm going to leave it as f of x. I'm going to add 12 over, and then I'm going to have 2, and when my leading coefficient of x is not a 1, I need to factor that out. So I actually have 2 times the quantity, x squared, and then factor out a 2 with the 4x plus 2x, and then plus some number that would make that a perfect square. And I get that number by taking half of the middle term, which is plus 1, and squaring it. So this number I put here is 1. So I'm adding 1 here, but to this whole side, I'm actually adding 2. So I need to add the same amount to the other side, so I'm also going to add 2 over there. So this is f of x plus 14, and now I have a factor of 2, and I'm going to factor this perfect square trinomial. So that would be x plus 1 in the parentheses squared. And then to just finish this off, I need to bring the 14 back over to the other side, and I would have f of x is now 2 times the quantity x plus 1 squared, and then minus 14. So in this form, I can easily tell that the vertex is at -1, -14. It's pointing up, and it is skinny because of the factor of 2. This next one is going to be a little bit messy because of our coefficient being negative, or a fraction. So I'm going to use the same format as I did up here. So I'll send the 4 over to the other side with f of x. So I'm going to subtract 4 here. And then I'm going to factor out a -3/4. And that would give me an x squared that now has a coefficient of 1 for my perfect square trinomial. Now, if I factored out a 3/4, I need to know 3/4 of what number would give me 9. So if I just think about that, 3/4 of what number is 9, I could make a little equation here. And then I know to get x by itself, I'm going to multiply it by 4/3. And this would be 3 goes into 9 3 times, times 4 is 12. So that middle term is going to be 12. And because I factored out a negative, it's going to be minus 12 because the negative times the negative is the positive. And then I have a perfect square number at the end, and that would be half of -12, which is -6, and I square that and get 36. So then again, I added 36 inside the trinomial, but I need to multiply that by 3/4 to figure out what did I actually add to this side. So -3/4 times 36, 4 goes into 36 9 times, so this is -27 that I added to this side. So I'm going to add a -27 to this side. So I have f of x, and I know this is a -31. I'm going to add that over in just a second, but I have my a term is -3/4. In parentheses, I'll have x minus 6. That quantity will be squared, and then I'm going to add over my 31. And here it is in vertex form. Number 2 asks us to describe all of the transformations that we get for y equals x squared that comes from this function. So because I have an x squared, I know this is going to be a parabola. And I know it's going to be pointing down because of the negative a value. Another way to say this is it's reflecting over the x-axis. It's going to turn down. The 1/2 is going to make it wide. The +6 is going to tell me that I'm going to shift left 6 units. And the -3 tells me I'm going to shift again down 3 units. All right, so here I'm going to graph this a little bit more precise than I did on, oh no, I'm just going to do a sketch on this one. Sorry, I was thinking ahead. So just a quick sketch on this one. My vertex is at -6, -3, -6, -3 is about right here. I know I have an axis of symmetry, and I know that it's going to be pointing down and it's wide. So it's going to look something like that. Number 3 asks us to find a maximum or minimum value. So this is one of those revenue problems, and they're asking, or they're telling us that the price and the quantity of a product follows this demand equation. So somebody did some supply and demand, and they came up with this equation to look at the number of items and the price to sell them. But remember, if we're looking for revenue, that equals the number of items times the price. So if I am going to express the revenue as a function of P, I'm going to take my X value and put in the expression that I know would represent X. So here my revenue is going to equal X, which is -5P plus 100 times P. Or I can say that this is -5P squared plus 100P. So this is my revenue as a function of P. Then they're asking us what price should be charged to maximize the revenue. So whenever we're looking for maximums and minimums, we need to find the vertex. That vertex point, those coordinates are going to help us determine what the maximum revenue is. So I'm gonna look for the vertex, and to get the x coordinate of the vertex, I have -b, which is -100, over 2 times -5, which is -100 over -10, and that would be 10. Now in our vertex, the x coordinate actually is the price, and that's what we just found. So the price is $10. So $10 is the price that we're looking for to maximize the revenue. And if this price, $10, is charged, we want to find out what the maximum revenue is. So I'm going to plug this $10 back into my revenue function. So my revenue is -5 times $10, whoops, -5 times 10, and then plus -5 times 10 squared plus 100 times 10. So this is -500 plus 1,000, and this would give me a maximum revenue of $500. Okay, so that actually would complete my vertex. So this is the maximum price that gives me the maximum revenue. Then in part D, they want to know how many of this product would sell at this price. So how many is our X value? So if I go back up to where it says X is negative 5P plus 100, P is the price. When I plug in the price, it'll tell us how many items we have to sell. So X is minus 5 times P is 10, plus 100, and we get a number of items that is 50. All right, so now on to the second part, where we are looking here to identify all these things on a parabola. So just looking at the function, we know this is going to open up because our a value is positive. Because it's opening up, it's going to have a minimum value, and it's going to be narrow because of the factor of 3. Now, to get the axis of symmetry, we really need to find the vertex. So for the vertex, to get the x coordinate minus b, so the opposite of negative 12 is 12, over 2 times a is 3. So this is 2. So the x coordinate of my vertex is 2, and the axis of symmetry would be the vertical line x equals 2. And then the y-intercept, the y-coordinate of my vertex. So to find y, I'm going to plug 2 back into the equation. So 2 squared is 4 times 3 is 12, minus 12 times 2, which is 24, and then plus 2. This is minus 12 plus 2 is negative 10. So 2, negative 10 is my vertex, and I want to do this a little bit more precise, and my numbers on my y-axis aren't very cooperative to plot the point 2, negative 10, so I'm going to count by 2's. So I'm going to say this is negative 10, here's negative 20, and if I do that all the way up on the y-axis, that's okay. I don't have to change anything on the x. They don't have to be measured in the same intervals. All right, so if I go over 2 and down 10, here's my vertex. And I can draw my axis of symmetry here. And I do know that my y-intercept comes from the c value in the equation, and that is 2. So on the y-axis, 2 would be right here, because remember we're counting in 2's. And if I reflect that over the y-axis, 2 spaces, this one is not right. We have a couple of guiding points. If I want to try another one, I might want to try x equals 5. If x equals 5, I have 25 times 3 is 75, minus 12 times 5 is 60, and then plus 2. So this would be 15 plus 2, and y would be 17. So that would be way up. 10, 12, 14, 16, 18, so about right here. And again, that's 3 units away from my axis of symmetry, so another 3 units would be over here. So this gives me a pretty good visual of what this parabola looks like. Our domain is going to be, for all parabolas, all real numbers, or I can use the funny little r. And the range, if I look at this, my range, my lowest value is -10, and then it's going to go up to infinity. If I look at my x values, I can keep going up and up. So my range starts at -10 and goes to infinity. Okay, and I would prefer that written in set notation. Number 5, we're looking at maximizing the area of a rectangular area to put a fence around. So I always draw whatever shape we're looking at, and I know that area is length times width. So here's my length, here's my width. I want to maximize my area. But I do know that the perimeter is 2 lengths times 2 widths, and the perimeter is 300. So if I were to factor out a 2 or divide all parts by 2, I know that the length plus the width has to equal 150. Now, if I were to solve this equation for one of these variables, I know that the length is 150 minus w. Okay, so if this is 150 minus w, and if I want to find the area, now I'll replace that in for my length. So the maximum area, or my area equation, I should say, is 150 minus w. So that represents the length, and the width would be times w. So if I were to distribute and kind of put this into standard form, I have minus w squared plus 150w. So this is my area function, and to find the maximum, I need to find the vertex of this function. So the vertex for the x-coordinate, minus b, so that's -150 over 2 times a, which is -1. And this is -150 divided by -2, which is 75. So in this case, my width is going to be 75. And if I plug in 75 for my width here, this is also going to be 75. So my length is 75, my width is 75, and the maximum area, if I plug this in here, would be -75 squared plus 150 times 75. All right, and I don't have a calculator handy. So -75 squared went and grabbed a calculator, is 5625. And then I'm going, and this is negative, plus 150 times 75 is 11,250. And if I subtract the 5625, I get 5625. And that would be, if I put my units in here, I'm looking at yards for length and square yards for my area. All right. And for the last one, we are looking at an inequality, and I have a quadratic function, and I want to know where are the values positive or equal to 0. So I need to solve this to find out where my x-intercepts are. So if I factor this, I'm going to have x plus 4 and x plus 1 equals 0. This is going to tell me where my x-intercepts are. So I have x is -4 and x is -1. So I'm going to have a closed dot on -4 and a closed dot on -1. And I want to know where in my domain would I have x values that make this function greater than 0. So I'm going to use the sign charts again. So I'm going to pick a number less than -4, like -5. So if x is -5, I'm going to put that in here, and -5 plus 4, that would give me a negative. -5 plus 1 would give me a negative, and this would be positive. So out here it would be positive. If x is in between these 2 points, let's do -2. -2 plus 4 is +2. -2 plus 1 is -1. So that's going to give me a negative value. And if I pick a number in this section like 0, 0 plus 4 is +4. 0 plus 1 is also positive. So right here, I have a positive number. So really what I'm looking at where this graph would be positive would be in the x values that I have highlighted here. And if I were to write that solution set, I have the numbers from -infinity to -4. So -infinity. And I'm including -4 because it does say equal to here. So I'll put a bracket there. And I also have this section over here. So I have a union of two sets, and I have -1, and then it goes to infinity. And it includes -1, that's why I gave it a bracket. And infinity, there's never a final value, so it always gets a parenthesis.